Hi everyone, this is Keith Devlin, Stanford University. I'm speaking to you from my home in Sonoma County, just north of San Francisco, California. I was disappointed not being able to be there last year for the conference because I was in the UK at the time as a visiting professor. I was looking forward to coming this year instead, but now here we are all having to stay at home because of this pandemic. So once again, I'm having to record a message for you. And on this occasion, I hope that I'll be able to answer questions in person when my presentation is done. And I want to begin by just asking you what you're doing now that you're sort of having to stay at home. Since I'm officially retired from Stanford, I've already had quite a bit of time on my hands. Now I've got even more time. So I've actually spent the time since March, when in California we were on essentially a lockdown situation, going through all of the possessions in the house, clearing out the garage, the basement, storage cupboard, taking everything that had accumulated over many years, sorting it out. I've got a fairly large pile of stuff on the driveway, waiting to be collected when it's possible to get things collected. And generally using the time to sort of take stock. I mentioned I'd retired. I retired 18 months ago. And it was a good time in my life anyway to sort out all of the stuff that had accumulated over decades and sort of give myself a fresh start. And I think that's an interesting position to take with regards to mathematics education. Perhaps what we should do now, given that we are having to sort of curtail the education systems in one way or another, do lots of teaching online and so forth, maybe now is a really good time to examine what we teach, how we teach it, and why we teach it. In other words, when we come out of this pandemic, maybe we will be in a position of being able to provide better mathematics education for everyone. So that's really the theme of the talk today. Reassess mathematics education with a view to revamping it, throwing out all of the stuff that's been in the mathematical education, whatever you want to call it, the mathematics education storage room, the mathematics education garage, the mathematics education basement, all of the stuff that's accumulated in mathematics education over decades. See if it's time to throw some of that away and restock and reinvigorate ourselves to the way we resume mathematics education after this pandemic is over. Okay, that's where I'm going to start. My theme is going to be mathematics making the invisible visible, because I want to pause and remind ourselves of what mathematics does, because we tend to think of it as a set of procedures for calculating things. And there's good historical reasons why we got to be there, but those reasons largely disappeared in the 80s and 90s. And that's some of the baggage we need to throw out of the basement. There's really I have three ways of thinking about mathematics. One is that it's the science of patterns. It's sort of search for certain knowledge and end to itself. And in fact, in 1994, I wrote a book, a Scientific American Library book with that title, as a deliberate attempt to, it's always worrying when you cough a little bit now because people run away. But this was a deliberate attempt to create a meme. It wasn't my phrase, it had been going around for a while. But I thought it was a nice meme, and so I wrote a book with that title to get people used to the idea that mathematics is about looking and analyzing certain kinds of patterns. Then there's the more familiar view of mathematics, that it's a toolbox for science, business, engineering, yada, yada, yada. And it is indeed a toolbox. It's an extremely powerful toolbox. It's a toolbox that has power for good and power for evil. And most people, that's their connection with mathematics. But then there's another one, which is thinking of it as a cognitive technology, a language in the more abstract sense of the word language, a language which makes the invisible visible. Again, I thought that was my phrase. I started using it, but then I realized other people were using it. So it's one of these things that was floating around in the ether, at least in the 80s, maybe the 70s. So these phrases have been tossed around. This, by the way, the beginning of this is actually a talk. These slides are pulled from talks I gave way back in 2001 to 2005. So I just took them and cleaned up some of the fonts. But it's basically stuff that I've been talking about for years. And some of you who've been to my talks or seen videos will have heard me say this kind of thing. It's something I've been preaching about for many decades now. But I want to spend today really focusing on this, that mathematics is a language and a cognitive technology. I wrote another book about that in 1998 called The Language of Mathematics, Making the Invisible Visible. I'm a books guy. I write a lot of books because I just like to think in large sort of chunks of stuff. And all the books I've written are basically written for myself as a 14-year-old schoolboy, because they're the kind of books that I did read at that age and that inspired me. And so I've been trying to do the same thing with these books. So that's my intended audience is me at 14 years of age. Okay. So this is using mathematics to make the invisible visible, which is another way of saying you're uncovering hidden structure or patterns. And so that's as I say, that's really what I want to be talking about. It's not unfamiliar to us to have tech. By the way, I'm using that word technology deliberately because it's something that you can use, and you can use it without knowing how it works. You just need to know the rules of how to use it. And so in that sense, for most people, mathematics is a technology. If you know how to use it and you can use it well, you don't need to go beneath the hood and see how it works in detail. And there are many technologies that make the invisible visible. The X-ray is an obvious one. It was actually when it came along, it revolutionized life because people got used to this idea that things inside themselves that had hitherto been visible because they were inside our bodies became visible. But that's not the only one. There are many more technologies that make the invisible visible. These are some of the more obvious ones. But they're all sort of physical devices, and they allow us to see inside things that are hidden for various reasons. Mathematics as a cognitive technology, as a framework for making things visible, does it in a different way, but it is still very analogous to those examples. For example, you look at an airplane in the sky. This one's either, I guess, coming into land, judging by the wheels down. You can see a lot of things there. What you cannot see is what's keeping that thing in the air. I mean, the wings and the fuselage and stuff are part of the story, but you can't see anything holding it up because what's holding it up are invisible forces. So there's something pushing up against gravity. Gravity itself is an invisible force. It's pulling it down. And there are other invisible forces pushing it up and keeping it in the air. You can see them with mathematics. In fact, that's the only way to see them. And we have aircraft because we have the mathematics that tell us how to build them to create those invisible upward forces. Here's another one. There was this comes from a famous study at the MIT Media Lab several decades ago now, I forget exactly when they were looking at what it is about beauty that we resonate to. And there are certain things that people around the world find very beautiful. Flowers are one of them. And it turns out amongst human faces, Denzel Washington is regarded as having one of the most beautiful faces. People resonate when showed images of different movie stars as to who they rank on an attractiveness scale. And it turned out that Denzel Washington came out almost uniquely above everybody else. And so the Media Lab did a study of the mathematics of the faces. And what they discovered was that Denzel Washington has a much higher degree of left-right symmetry than almost any other person around. And so what we are resonating to, amongst other things, when we rank Denzel Washington as more attractive than other people, is left-right symmetry. And in the case of a flower, it's not just left-right symmetry, it's symmetry about any radius. So part of what constitutes beauty, which is sort of built into our perceptive system, is in fact a resonance with symmetry. Mathematics provides the tools to not only analyze the symmetry, to analyze the photographs, but it provides a branch called group theory, which in a sense is the abstract study of symmetries in general. And it was group theory as a theory of symmetry that ended up forming the basis of most of our modern theories of physics. We talk about breaking the symmetry in the universe. That's essentially a group theoretic concept. So group theory is a branch of mathematics that allows us to analyze symmetries in a very abstract sense. And then another one, which is an obvious one, is when people talk on cell phones, and I've deliberately clipped the original images from when I gave this talk a couple of decades ago almost, of very early mobile phones and laptops and things, because we know that people can talk at a distance, We know there's no cables between them. Even if there's a cable between them, we can't actually see what's going between them because it's electrons. But in this case, the only way to understand what's passing between those two people is in terms of mathematics, the mathematics of various kinds of waveform, et cetera, et cetera, et cetera. So with mathematics, we can see in great detail those things that are invisible to the degree that we can build and develop those technologies. It's not just that we can see things that are invisible, it's because of the mathematics that we can build those invisible things and use them. And this is huge, and this view of mathematics tends to get overlooked because we focus so much on procedures. Before I get onto the procedures in detail, the question is, why are there all those symbols? And the answer is that you need an abstract notation to describe the abstract patterns. So if you're describing something abstract, you need a notation specially designed to capture the abstractness. Incidentally, the mathematics on the left actually came from a paper on computer graphics, actually from the movies. That's CGI. That's some of that actually, I think, if I remember right, came from a paper from Industrial Light and Magic or Pixar or one of those companies. So that's mathematics that allows us to put images on screens. And the reason I picked that piece of mathematics was because I wanted to show that this abstract view of using symbols actually has applications in the arts, but that's nothing new because music is an abstract notation that we developed precisely to be able to specify, define, understand, and follow the abstract patterns of music. So there's a familiar symbolic language that captures abstract patterns. Those are the abstract patterns that our ears pick up when we listen to and appreciate music. And as I say, the one on the left actually turns out to be the specification, not of music, but of images on a modern movie. Another couple of examples. Here's some more mathematics. That's part of the mathematics that allows us to see those hidden forces. It's not all of the mathematics. It turns out that that flight is actually rather complicated. None of the simple models capture everything. It's a very complicated phenomenon. But Bernoulli's equation, that piece of classical mathematics from a couple of hundred years ago, allows us to see some of the forces that keep the airplane in the sky. I think I first gave this talk in a tour of Italy, which is why you have the Alitalia pictures there. Another example, how does this store music? How does iTunes or any other digital storage store music? Well, it uses certain kinds of mathematics, including what we know as Fourier series and discrete waveforms. So there's some classical mathematics, at least a modern version of classical mathematics. That's the mathematics that allows us to store music. And then one more, here's another example. That mathematics may one day save your life, and for some of us may have already done so, because that's part of the mathematics that you develop in order to study how the human heart works. So there's these abstract mathematical formulas, these derivations, these proofs, these solutions, which really connect to the real world and have significant impact. And so that was all a sort of a recap of stuff I've been talking about for several decades now. From the rest of the talk, I want to focus on the today. As I say, we have an opportunity to clear out the basement and the garage, get rid of the old stuff and start focusing on the new stuff. We can't throw away some of the old stuff. I'm not suggesting we throw everything away. I haven't thrown away everything from the garage, but I kept the things that I thought, yes, I probably do still need this. Okay, so there's the what and the why and the how of teaching mathematics today. And before 1965, that's really how mathematics was done on a large scale. We had computers, we had an internet, we had a network of computers, but it was a human network. There were large buildings full of men and women. Actually, I think they tended to be dominated more by women than men in that particular domain. There were the sort of the hidden figures from the NASA movie that were there, unacknowledged, but doing all of the work. But before 1965, that was really how mathematics got done. You sat there with a paper and pencil and you ground it away. More recently within that era, if you look in the bottom right image, you'll see some desk calculators. There's a big one in the front. I think it's a Marchant, which I used early on with my first job as an intern from high school. There were mechanical driven, electrical driven, and then eventually digital devices to help with the arithmetic. but it was still done largely by people. So you couldn't get into mathematics, you couldn't use mathematics, you couldn't be a mathematician unless you could do those calculations. And this is really why we tend to think of mathematics as revolving around calculations, because for generations, actually for centuries, it did. You had to do those calculations yourself because there was no other way to do them. Okay. Sometimes the calculations got very complicated. This is a famous picture, I guess somewhat artifactually created for the photograph, but they did have these blackboards apparently. This was at NASA when they were doing the calculations for spaceflight, and they had these very large blackboards with calculations on. But it's the same idea. It's just writing abstract formulas down to do something. But this is where this was the equivalent of a supercomputer, if you like. But then after 1965, a lot of the computations began to disappear inside machines because we had digital calculators coming in the early 1960s. We had digital computers starting to do the industrial strength computations. So since 1965, doing the calculations increasingly went underground and was outsourced to machines, which meant humans could spend their time doing things that machines couldn't do. And in fact, that's what's happened, because in the world of professional mathematics or engineering or science in general, none of us in the business, and this is the case since the early 1990s, none of us in the business almost ever solves an equation by hand, draws a graph by hand, or does any of that stuff by hand. All of the stuff that I learned up to my sophomore year at university essentially became obsolete at the end of the 1980s. Obsolete in the sense of I was never going to actually do that again. Not obsolete in the sense is I do every day use my knowledge of what those techniques can do. So it's not that we have to throw away calculation, it's just that the focus now isn't on doing calculation, it's knowing how to do calculations using devices. And you can't do that unless you know something about what's going on under the hood. So the focus of mathematics education has to, and in many cases has changed from mastery in order to execute to mastery in order to understand sufficiently to use the technologies that do the execution. My favorite is Wolfram Alpha because it's so simple. There's Wolfram Mathematica, there's Maple, there's MathWorks, MATLAB, spreadsheets, calculators. I've deliberately left in the paper and pencil because it always happens. You start using the technologies and then you have to do something to link them to something else. So the old technology hasn't gone away, just as the old knowledge hasn't gone away. It's just that we don't have to spend hours doing calculations. Accuracy no longer matters to me or to a human because the machine does it. What does matter is being able to recognize that something's gone wrong because the answer is out by an order of magnitude or a certain factor. So the skill set has changed from having to be able to do a calculation to having to be able to safely and effectively use technology to do it for us. We're still in the process of reinventing mathematics education to do that well. So going back to that original slide, if we look at those three views of mathematics, the one in the middle, I think we can grey out now. It hasn't gone away, but it's a toolbox that really is a toolbox now. We have tools that we can use by pressing our fingers on screens or keyboards and so forth. So that's sort of gone away, and it's just under the hood. Okay, so that means what do we have to do now? We have to learn how to teach mathematics as a language and a cognitive technology. How do we do that? How do we prepare people in order to sort of live in a world where the computations are done for us, but the technologies are dumb? You have to tell them what to do, how to do it, not necessarily always how to do it, but certainly what to do, when to do it, and you have to be able to see if the answers are more or less what they should be. Because people still make mistakes and machines occasionally do weird things. So it's the what and the why and the how now of mathematics in this sense of understanding the world. There's a view of the invisible that literally stopped our world. There was this invisible thing moving around. The only way we could see what we were facing was by drawing graphs. And this, seeing the invisible with graphs, which have been around a long time, that was so dramatic that in a period of about 48 hours, the world changed dramatically. And it was by allowing us to see the invisible. And it was by drawing those graphs. That particular set of graphs came from this paper from Imperial College. 16th of March was my birthday, and I celebrated my birthday by knowing that we were about to go, because I can read graphs. And I saw the graphs in the newspapers coming out on Twitter, and I dug around and got hold of a copy of this paper, and it was dramatic. I mean, that was the most interesting birthday present I've had for a long time. And this was the one that in particular made the US and the UK decide to change their strategy and go into social separation. Actually, California had already done that, at least in some counties, starting in Santa Clara. So seeing the invisible allows us to do things. You know, we are now operating our world because we can see this invisible thing. We still can't see anything other than graphs. Here's another one that came up. This was an image that came up very early of the possibility, you know, going by seeing the invisible, of being able to look into the future. This was looking into July back in March, and knowing that if we didn't do something, we could be in this kind of a catastrophe, and that if we did do something, we could be in that kind of a catastrophe. So we were able to see the future. We were looking ahead to the future and see what was ahead and be able to make wise decisions. And let me make an observation about that. This is actually not about providing answers. There was an awful lot of sort of debate in the news media about whether the answers are right. This wasn't about right or wrong answers. We didn't have the data to plug in accurate numbers into those graphs. We didn't have anything other than knowledge about exponential growth and some knowledge of epidemiology and been able to look at sort of rates of transmission and so forth. So we had some basic ideas, but we had no real data to go on. And so this wasn't about providing answers. And mathematics in the real world is almost never providing answers. These days, if you have a problem in the real world, and I've done a lot of consulting for the US Defense Department and for industry over the last 20, 30 years. And so I've actually worked in these domains. It was almost never, ever about providing answers in the classical sense of do a calculation and come up with a number or an equation or something. It was about providing information that help experts make better decisions. And almost all mathematics now, as it's used in the real world, is about optimizing, doing something better, safer, faster, quicker. That's what it's all about. That's what Google does. Google is an implementation of a mathematical algorithm that does search better. It allows you to find information quickly that's better meted to the needs based on a few keywords. I mean, that came out of Stanford when I was at Stanford, and it was kind of amazing that these two graduate students, a couple of 100 meters away, had come up with this incredible idea. With hindsight, it was quite a simple idea. It was 19th century mathematics, but it wasn't about getting right answers. It was about getting accurate, about getting more accurate answers or more optimal answers, better answers. Google doesn't always give you the answer you really wanted at number 1 or number 2, but it usually does it within the first 5 or 6 because it puts the focus on optimization. Incidentally, Google was obtained by thinking about the users, not so much the structure of the language. And here's another example of how looking at the invisible can help make decisions. Just the way you represent graphs can turn one situation into another situation. Exponential growth is kind of weird. And so it sometimes looks as though one nation is worse state than another state. But by looking at the log graph, you can see that on this particular graph, which goes back to early February, to mid-February, Italy, which had had this steep growth and looked to be getting much worse, was actually getting much better because the slope was going down, the acceleration was down. And the US was, although it looked safer, was actually going in the opposite direction. And it was the way you can look at them. The graphs can be done in different ways, and depending on how you do them, you can get that information. But it was the people that made the decisions. It was actually the politicians and the medical people that together got together and made those decisions. All of the mathematics did was provide visualizations, and everybody knew that none of these graphs was necessarily accurate. They couldn't be. There were different models producing different things, but the information was that was going in, the data was just too sparse to have any real confidence in these things. What you could have confidence in was that the graphs are the right kind of shape. You know, how high they are, how wide they are, that was another matter. But they were the shapes, because that's just exponential growth of a virus. And then there were various, this is from the University of Washington Institute of Health Metrics Evaluation, I think it's called. One of these university-housed organizations that does work. This was the one that the US and the UK made quite a lot of uses. Since I've got family in the UK, I was looking at the UK back when I took a screenshot of this. This, I guess, was April the 13th. And I was just looking through, and it was a very nice representation. Incidentally, I feel fine showing these kind of representations to this audience. And in principle, they would provide wonderful examples, because these are nice interactive tools for using in classrooms. My own view is I would not use this in a classroom of school children, because who knows what their personal circumstances are with regard to the pandemic. And it might be awfully traumatic to start looking at these figures if you're in the thick of this thing. But there are lots of other domains. I'm just using these because they're in the moment, and this is an adult audience. And with hindsight in the future, these kind of tools are wonderful tools for exploring data. And again, it was to decide decision making. You know, I've got friends in New York. I live in California, so I was daily comparing the graphs between California and New York, and none of the numbers were necessarily accurate, but one thing that was clear just by eyeballing it was that New York was in a much worse situation than California was, for a whole variety of reasons. So, you know, I felt somewhat relieved to be here, but very worried about people I know in New York and New Jersey. And it was just about reading them. So I think a hugely essential skill, and this was true before the coronavirus pandemic, is just being able to eyeball these things, because eyeballing is what it comes down to. This is number sense. It's a graphical version of number sense. The numbers themselves, you cannot be relied on, because the data that goes in is not accurate. It's all lots of estimation. But the shape of the graphs is something we can lean on, and we can make decisions. You know, that one image says, if you have equipment in California, send it to New York. And in fact, the governor of California sent 500 ventilators mostly to New York, because he could see at that stage that New York was in a worse situation. So coming back to this question, the what and the why and the how, the what is now, I think, pretty clear. It's teaching for the kind of tools you need to be able to absorb and act on the kind of information that those graphs displayed. If you can't read a graph and eyeball it, you can't make the right decisions. You know, I sometimes worry about governors that want to open up their states quickly. Is it that they are not sufficiently numerate to be able to read a graph and say, whatever the numbers are, this is worrying, because the slope is getting steeper. So you have to be able to just eyeball those things and understand them. So it's a form of number sense. The why is clear. I mean, that example is dramatic in that we cannot, as a society, a global society, we can't go forward without thinking of the information, considering the information that is invisible except through the language of mathematics. Mathematics is our only eye, our only way of seeing the dangers that are out there in the world, being passed from person to person, from gas pump to gas pump, as it were. You know, it's the world we live in. So the question remains, what about the how? How do we teach mathematics in a way that prepares people to be able to deal with this onslaught of information? And this is big data. We're talking about how to make sense of big data where the underlying numbers themselves will have all sorts of errors in them. So how do we do that? And these are just ideas I'm throwing out of ways we might want to do that. I mean, this is a new world. It's literally a new world now, especially for those with education. So how should we be thinking about what we do? Well, certainly there's number sense, which interestingly enough, when it was introduced in 2001, was as a way to help people with learning disabilities learn mathematics. Well, it turned out that if you do the things you need to help people with learning disability, this is the original definition in the paper from these guys, somewhere in Texas, I forget the university. And it's just a general sense of of numbers. I've been a numerate sort of person. That's crucial. As far as we know, the only way to get it is by doing a lot of calculations yourself. So this is one of the arguments that say, yes, you still should learn how to do arithmetic and know about these things, because I don't think we know of a way to get to number sense without doing lots of calculations. Most of the famous mathematicians in history spent a lot of their youth doing calculations, and that seems to be essential. You certainly need general deductive reasoning skills. You certainly need creative problem-solving ability. Algorithmic reasoning is certainly important. Metacognitive skills, solving problems. The phrase that's tossed around today is that the big problems we have to deal with are wicked problems. They're not encapsulated. They don't have unique right answers. They are complicated and they're multidisciplinary. And that's certainly the case with epidemiology. And then data science, ways to present data. We have people who know how to do that, but the rest of us in society need to be able to interpret the data when it's presented in a whole variety of ways. And if we can't look at these images and see what they mean in the same way that a musician can look at a musical score and understand what it is. I actually can't read music, but I know that musicians can read music, the ones that can read music, and they look at a score and they hear the music. They know what it means. I can't read music, but I can read mathematics and I can read graphs. So I can glance at these things and I can get a good sense. And in today's world, everybody needs to be able to do that. There's an argument that says, I've done okay because I can't read music, but I don't think you could say you'll be okay in the world if you can't read these kind of abstract symbols. So it's not doing the calculations so much as understanding what they mean and what they give us. And there's a degree to which you have to do some hand grafting mathematics to get to that stage. And there's other things. So those are the hows of what we need to sort of do. That I think is important, especially in today's world, to keep uppermost in our minds when we're teaching that this is the goal. This is absolutely the goal we're going for. Focus on the thinking and not the computation. Yes, we have to do some work on computation because you can't get those number sense skills without doing computation. You have to get a good sense of numbers and of shapes and graphs and things, and you handwork those to do those. But you're not learning that stuff. You're not going through that to do it because the machines do it faster, better, quicker, more accurately, and with bigger data sets because the problems of today's world involve huge data sets. So the calculations are always going to be done for us from now on. So the focus has to be on the thinking. But the goal is being able to be a productive and a safe member of society. And in today's world, this is essential. We can't get away from that anymore. We have to clear out the basements of mathematical education and keep the things that are absolutely still essential, the tools. And I've kept some of the tools that I found in the basements and the garage. I know I might still use them, but most of the junk I just threw away. And I think now's the time to do that in mathematics education. Okay, that's what I wanted to say. I'm now sitting here ready to answer any questions that you have, either directly related to what I said, or else something else that's on your mind that you'd like to spend a few moments talking about in this conference. So the floor is yours.